You open your browser, you type www.youtube.com, you hit enter. That's it. That's the trigger. One keystroke, and a system spanning thousands of servers across dozens of countries begins assembling an answer to a single question. Where is this? And it answers it, usually, in under 100 milliseconds, often far less. In this video, we're going to slow that 100 milliseconds down and watch it frame by frame. Every step, every decision point. By the end, you'll have a single, unified picture of how naming actually works, not as a collection of separate concepts, but as one coherent system doing one coherent job. Let's start the clock. The moment you hit enter, your browser does something before it touches the network at all. It checks its own memory. Modern browsers, Chrome, Firefox, Safari, maintain their own internal DNS cache, completely separate from anything the operating system manages. If you've visited YouTube recently, or if any tab in your browser loaded a YouTube resource recently, the browser might already have www.youtube.com cached with its corresponding IP address and a TTL that hasn't yet expired. If the browser cache has a valid entry, a hit, the resolution is done, right there, before a single packet left your machine, before your operating system was even consulted. The address is known. The browser moves on to making the connection. This is scope and caching working together at the smallest possible scale. The browser's cache is locally scoped. It's private to that browser instance on that device, and it exists purely to avoid repeating work that was recently done. It trades freshness for speed, exactly as every cache does. If the browser cache misses, either because the entry doesn't exist or because the TTL has expired, it passes the question down to the next layer. The browser asks the operating system, what's the address for www.youtube.com? The OS has its own resolver, the stub resolver, and its own cache. Before going to the network, the OS checks here. On most systems, you can actually inspect this cache directly from the command line. It holds recently resolved names from any application on the machine, not just the browser. If another application resolved www.youtube.com in the last few minutes, the OS cache might have the answer even if the browser cache doesn't. But before the OS even checks its DNS cache, it checks something else, the hosts file. This is a small, static text file on your machine, one of the oldest naming mechanisms in computing, from the era before DNS existed. It maps names to addresses manually, line by line, and it takes priority over DNS entirely. Most users have never touched their hosts file, but developers use it constantly to redirect a production domain to a local development server, to test a new deployment before it goes live, to block domains by pointing them at a dead address. If www.youtube.com appears in your hosts file, the OS returns whatever address is listed there and never touches DNS at all. The entire resolution system is bypassed by a text file. This is scope in its most extreme form, a name whose resolution is overridden locally, visible only to that one machine, invisible to every other device in the world. If the hosts file has no relevant entry and the OS cache misses, the stub resolver sends the question to the network, specifically to the address of the recursive resolver that the OS has been configured to use. That configuration, which recursive resolver to ask, was set when your device joined the network. If you're on a home network, your router handed it to your device via DHCP when you connected. If you're on a corporate network, the network administrator configured it. This is the scope mechanism operating invisibly. The network you're on determines which resolver you use. The resolver you use determines which namespace you're looking into. A corporate network points you at an internal resolver that knows about internal resources. A home network points you at your ISP's resolver, which only knows public DNS. The same query sent from different networks goes to different resolvers, potentially getting different answers, all by design. Your query arrives at the recursive resolver. What is the IP address for www.youtube.com? The recursive resolver checks its own cache first. This cache is shared across everyone using that resolver, potentially millions of people. www.youtube.com is one of the most visited domains on the internet. The chance that another user resolved it moments ago, warming the cache for you, is extremely high. If there's a valid cached entry, the resolver returns it immediately, and your browser has its address without any authoritative server being contacted at all. If the cache misses, either because the entry genuinely isn't there, or because the TTL expired since the last query, the recursive resolver has to go find the answer. This is where the resolution machinery kicks into gear. The recursive resolver begins walking the delegation chain. It already knows where to start because of a process called priming. It came preloaded with the addresses of the root name servers, and those addresses almost never change. It contacts a root name server. I'm looking for www.youtube.com. Help. The root server doesn't know the address. What it does know is every top-level domain on the internet and which name servers are responsible for each one. It looks at www.youtube.com, sees that it ends in com, and returns a referral. Here are the name servers for the com TLD. Go ask them. The recursive resolver almost certainly has this referral cached already. The delegation from the root to the com TLD name servers changes extraordinarily rarely and is cached with long TTLs. In practice, the root is often skipped entirely for common TLDs. But conceptually, this is where the chain begins. The recursive resolver contacts a com TLD name server. Same question, same structure. The TLD server doesn't know the full answer either. It knows who's responsible for youtube.com. It holds the NS records that YouTube's domain registrar filed when the domain was registered. It returns another referral. Here are the name servers for youtube.com. Direct. Go ask them. Again, the recursive resolver has likely cached this referral from a previous resolution. It doesn't query the TLD for youtube.com's name servers every time, only when that cached referral has expired. Now the recursive resolver contacts one of YouTube's authoritative name servers. These are servers that Google operates, holding all the DNS records for youtube.com and its subdomains. The resolver asks, what's the address for www.youtube.com? Here is where something interesting happens. www.youtube.com almost certainly doesn't have a plain A record pointing directly to an IP address. It very likely has a CNAME record, an alias pointing to another name. Why? Because YouTube serves users all over the world, from servers in many different locations. The address that makes sense for a user in London is different from the address that makes sense for a user in São Paulo. A single static A record can't accommodate that, but a CNAME pointing to a name controlled by Google's or a CDN's intelligent routing infrastructure can, because that second name's authoritative server can return different addresses to different resolvers based on geography, load, and network conditions. So the resolver gets back a CNAME. It follows it. It now resolves the canonical name, which might return yet another CNAME, or might return a set of A records with IP addresses. Each step in that chain is another lookup, potentially hitting cache at each stage, potentially requiring another query to an authoritative server. This is name aliasing, doing real work, invisibly, in the resolution of one of the most visited domains on the internet. The address you end up with is not directly stored under www.youtube.com. It's reached through a chain of indirection, each step managed by infrastructure designed to route you to the best possible server for your location and conditions. Eventually, the chain terminates. An IP address, or a set of them, comes back. Let's say it's 142.250.74.206. The recursive resolver packages this answer and sends it back to your OS stub resolver, which passes it to the browser. Each layer caches the result with the TTL attached to the record, so the next lookup, by you or by anyone else using the same resolver, goes faster. Your browser now has an IP address. The naming system has done its job. What just happened? Root to TLD to authoritative, CNAME chain followed, answer cached and returned, happened in somewhere between 20 and 120 milliseconds for a cold cache and in microseconds for a warm one. Now consider everything that could have gone wrong along the way and how the system handles it. If your browser cache had an expired TTL, it moved to the OS cache, a fallback. If the OS cache was stale, it queried the recursive resolver, another fallback. If the recursive resolver's cache was expired, it walked the delegation chain, another fallback. If one root server didn't respond, the resolver tried another, redundancy. If one of YouTube's authoritative name servers was unreachable, the resolver tried the others, listed in the NS records, redundancy again. The system is layered with fallbacks, not because any single layer is unreliable, but because the combination of layers, each catching what the previous one misses, produces overall reliability far exceeding what any individual component could achieve alone. And when fallbacks are exhausted, when the resolver has tried every authoritative name server and none responded, or when the delegation chain has a gap, or when the domain registration has lapsed, the resolution fails. The browser gets back NX domain, or a timeout. Server not found. When naming fails, everything above it in the stack fails too. Let's pull back one final time and look at the whole picture. You typed www.youtube.com. That string of characters traveled through 5 distinct naming layers before a connection was ever made. It was checked against your browser's local cache, the narrowest scope, the fastest possible answer. It was checked against your OS cache, slightly broader scope, still entirely local. It was sent to a recursive resolver configured by your network, where scope is determined by which network you're on, and where caching serves millions of users simultaneously. The resolver walked a 3-level delegation hierarchy: root, TLD, authoritative. Each level knowing only its own piece of the namespace, each referral moving closer to the answer. And the authoritative answer came back through an alias chain, routing you not just to YouTube's infrastructure in general, but to the specific instance of that infrastructure best positioned to serve you. One URL, one enter key, the entire series in 100 milliseconds. This is what naming is. Not a feature of DNS specifically, not a quirk of how the web works, but a fundamental layer of abstraction in every networked system ever built.